So good evening, dear faculty and students. So welcome to the lecture meeting series of SAEISS Trichirappali division. So now today we have Dr. V. Anandakrishnan, Professor, Department of Production Engineering, National Institute of Technology, Trichirappali, is online. And we have a very interesting topic, the challenges in additive manufacturing for automotive and aerospace applications. So Dr. Anandakrishnan has a wide knowledge in additive manufacturing, and he is going to share his experiences and expertise with us all in this August gathering. Now I request Dr. Anandakrishnan sir to handle this session.
Sir, good evening and good evening to everyone. Am I audible, sir?
Yeah. Yes, sir. Yes, sir. Please, sir.
So, with great pleasure, I would like to extend my thanks to Professor Arumuli Chelvan, sir, for providing this an excellent opportunity to give a talk, give a lecture in this SAE India Southern section. Hope I will try the best to provide some of my experiences, what I faced in the past last 7 to 8 years of my working with additive manufacturing. Let me start the presentation. So first I would like to say, since the talk is, I will be covering some of the contents with the aerospace as well as automotive. So why India wants a Rafale? So if you see in the way, right, as because this was some of my thinking, what I grabbed from the day-to-day affairs when I see some television. So there was out of the content of politics, we have to think about as an engineer. If you think about why India wants this Rafale, we bought a Rafale. We have bought few Rafales, right? And nearby, I have shown something our indigenously developed. Tejas aircraft. Actually, this Tejas aircraft is a light compact aircraft, LCA, indigenously designed by Aeronautical Development Agency, Defense Research Development Organization, and it is manufactured by Hindustan Aeronautics Limited. There are a lot of DRDO labs being utilizing, making a lot of research in this, building the total mission, flying machine. In that case, but if you see in engineering, has also take part some of the financial things. When you think about the economy of buying a Rafale or making our Tejas, there are a lot of comparisons being done in the World Wide Web, and you can you have the liberty to, you can Google and find out what is the difference between the Rafale and by performance and about Tejas also. So in a way, if you see some websites that some rating has been given. The one is they are providing, when like LCA is considered, Sweden's SAB or LCA Tejas comes second, and Pakistan is JF-17 Thunder comes third and fourth. These are some rating depending upon some of the performances and other things like maximum weight it can carry, and what is the range it can cover, and what is the maximum speed. All these things put together. But at at an end, right, when you think about for the cost of buying one Rafale, ourselves we can produce more than 4 Tejas. That is how, because why? Because we are not going to buy something else, only the material, not only the engine, not only the machine, but we are also trying to, we are going to pay for the technology behind that one. At the end, if also think about the engine, we have a Tejas aircraft, but the engine is not by our defense. So the engine development is it's far away, going in very quiet, very long time. It's being going there, but it's not so easy for a flying machine to get certified for any engine. So General Electric's engine is now being used in the Tejas. So it is something. I was also working with basic engineering, doing PhD research. Everybody know about that. When academic researcher is supposed to, most of the time we used to do in IITs or NITs, we used to do some research based on basic research where new material has been developed and the new technology by which the material can be converted from one form to another so that it will be useful for the society. But in that case, this was some of the enlightenment when I was surfing through some of the things, right? I have a very good friend working with GTR in Bangalore. When we were discussing, I come to know about, and also I attended some of the lectures delivered by DRDO scientists. Then I come to know about DRDO scientists. Then I come to know about all the things. Right? Right? That is right. So in that case, right? So what is the main thing, right? Either it may be an aerospace component or aero engine or a Audi's three-dimensional 3D printed engine in an car. In that way, the importance is of manufacturing is very, very important. So why manufacturing is very important is when countries are being compared for whether it's a developed country or it's going to be developed. In that case, what you can easily see is the manufacturing, the ability to manufacture is very, very important to make any country as a developed country. So for a small example, if you say India has become one of the top country by manufacturing the vaccine in a very shorter time. When COVID pandemic was occurring, and you see India could manage to manufacture all the vaccine vials in a very high rate of production. So the ability to manufacture such kind of a vaccine in a clean room technology where it should not get any contaminations. That's why India has shown. Now you know about the importance of India and how India is being given a friendly handshake by most of the countries because of the manufacturing ability, which helped them to come across these kind of issues. And when you talk about manufacturing, so the concern is about raw material we may have or not, right? We are very luckily India has plenty of raw materials available with the Mother Earth, and the conversion of this raw material into any product which can lead to profit. If you say there are a lot of technologies like laser beam, electron beam, ion beam, artificial intelligence, automation. All these forms, these things add value to the compound. So in this point, it's not by mere assumption. I'm not saying that. I come across some of the books where it's been discussing about the ability, why manufacturing. So manufacturing, despite its decline in 1980s, you see UK and US became the fully developed countries in those years. Why? Because a lot of millions of people were directly involved in manufacturing in these countries. Some statistics says from 1999, what they say, 20% of the accountability of GDP for UK has been given by 4.3 million people. Likewise, if you see US, 17.8 million people were working. Now the scenario has a shift. We don't want the number of hits of people need to be counted. We need to know about automation is there, full of automation, fully automation. You can manufacture any kind of things with the technology with reduced manpower. That is another scenario. So it doesn't mean now more the people, the country will become a developed country. Now any country which is having the capability to automate industries or industry 4.0, or they want to give the highest productivity by means of manufacturing with all the manufacturing technology, then that country will become a developed country. So in that way, so what quickly manufacturing, right? Quickly manufacturing. This is this is a traditional method. Actually, there is a small misunderstanding by the young engineers. What they actually feel is something like 3D printing is something a heavenly process. You can do any kind of component can be manufactured by this particular additive manufacturing. So I'm not going to say or accept such kind of a hypothesis. It is different actually. This additive manufacturing is existing in the earlier olden years, but in of a different form. Now the technology upliftment has given it a new era where additive manufacturing has found its shift over the replacement of a lot of different kinds of processes. But so what do we do in the first process A in the top line? What you can see here, a material, a raw material of a bigger size is taken, and we do some subtractive process. The subtraction may be by conventional machining, or sometimes it may be by laser or electron beam or ion beam, any kind. We remove some material, and finally we end up with this particular product, and leaving out the removed material as waste. Whereas the second process, the process B, you can see here, you have a system or a developed technology by which a powder or something else, a wire of material can be used to make layer by layer addition, thereby getting any kind of a three-dimensional object with quite a little amount of waste. This is how the technology is playing a vital role in the current scenario of manufacturing. So simply speaking, additive manufacturing is an appropriate name given for a layer by layer building of material. It may be the material may be of plastic, metal, concrete, or any time, right? In near future, as like a scanning of a CT scan can scan anybody's lung or something else. And if you have the material, biomaterial to manufacture any lungs of a human, and if you have a technology to deposit layer by layer that material, you can create any complicated shape, even the very fine details of the alveoli sacs and your lung, whatever the airways, everything can be easily scanned and can be 3D printed. The scenario is very shortly we are going to face that or see that also. So to make that, you need a 3D model of the component. Whatever the component that we are going to manufacture, we need a 3D model. So there are plenty of sophisticated software are there, and there are even reverse engineering by which we can scan, make a 3D cloud data and convert the component, create the component in any kind of a three-dimensional object. Once these three-dimensional objects are obtained by means of a CAD model, we go for a layer by layer slicing, and these sliced data will be given as an input to a additive manufacturing setup where the manufacturing can be done layer by layer. So this is how the additive manufacturing. So there are majorly, if you see some process additive manufacturing category, one category is powder bed processes. So here either the powder will be, powders means small particles of materials. That particle to particle attachment are made either by a laser source, either sintering. Sintering means not melting into molten state, but a semi-solid state. You can heat one particle, another particle attached, or sometimes we can melt by laser melting, or we can go for an electron beam melting. So either by applying different kinds of technology, you can melt a small particle and you can join particle to particle to create one layer. Once one layer is being manufactured, then what else we do? We go for the next layer. So layer by layer additive manufacturing can be done by powders. When talking about the materials feasibility to do this kind of a process, it can be used by either any kind of a plastic, elastomers, or ferrous, non-ferrous material, anything can be done. The second major category is material deposition processes. Here, the material, maybe sometimes it may be by a powder, you can blow the powder, right? You can have some space, you blow the powder, and then you define whatever the cross section that you want for one layer, blow another layer of powder, you can create cross section. So there are plenty of techniques available for additive manufacturing. Even a lot of new processes are being developed and being patented all over the world. Then again, we can create a wire, extruding a wire, and then we can melt the wire to a semi-solid condition, and then we deposit whatever the shape that you want, and you can create a three-dimensional structure. We call it as free forming also. Sometimes we can go for an extrusion process. You can have some metal pellets, make the pellet go through a nozzle or an extrusion chamber. It extrudes, it makes into semi-solid condition, create a molten condition or semi-solid condition of wire material, and then we can deposit. Here also there is no limit about the types of material what we use, ferrous, non-ferrous, or thermoplastics. Any kind of things can be done. So just I want to differentiate a powder-based process and a wire-based process. In a powder-based process, we have very small components can also be made, right? Usually some small components, because when you imagine about you are going to print a large engine block of a four-wheeler. So that engine block size, what will be the volume of powder? Those powder are to be procured or to be manufactured by some other process. I will tell about those processes in future slides. So the components are limited to small, and then very fine filigree structures, very small intricate shapes can be manufactured in this powder-based process. And parts are very near to the final shape. And you see, utilization will be all around approximately 70%. Remaining, because we handle the powder, we spread the powder, we use some beams. I will show some videos also how it works. And it's a slow process because particle to particle are to be welded by means of a laser or electron beam, and high price of powders because of the purity and the size and types of the powders need to be used. It will be very expensive, And there is another advantage is the reuse of the powder. Once the component is being built, the remaining powders you can take it, sieve it, and you can categorize the powder for some other process, and again you can use this one. When we talk about wire, it's a free space process, right? You can simply make the wire, you can deposit the wire whatever the shape that you want. So big workpieces can be manufactured and post. But what happens when you do layer by layer deposition or done? What you see, imagine you see here, right? We have made some metal deposition by means of an welding process. So one layer if I deposit, another second layer if I deposit, what happens? The first layer is again heated. So when I do the third layer, the first and second layer are being heated. So again and again, if you heat, you can also see the distortion in this base, even if it is a very thick plate or substrate over which we did the welding depositions. So you cannot avoid such kind of heat conduction, convection, and radiation to the nearby layers. So normally you will have non-homogeneous grain structures, metallurgical uniformity may not be there at the time. So you need to go for some post processing. That is one. Another form is when you are going to deposit with these wires. So you may not be having the proper exact shape of what you want, right? There will be some weaveriness, right? If you see, there will be weaveriness. I'll show you another bigger workpiece over here. A job made of a larger deposits rather than you can see over here. Sir, am I audible now?
Yes, sir.
Yes, Professor. Yeah.
Yes, sir. Sorry, sir. I had a network drop. Right.
Okay. Fine.
I have to connect it. So, my video visible, sir?
Video not.
Yes, sir.
Yeah. This is fine. Yeah.
Yeah. So here, if you see this here, when you go for a multi-layer deposition by means of a wire-based deposition process, you can see these layers are not quite good in the surface finish. You have lot of extra projections. So this is not it is not a good idea to have the shape, right, exactly with this whatever the shape. Like the control over a powder-based process is quite very good. Whereas this kind of a process by a wire-based additive manufacturing, you need to go for post-processing, one for your geometry, as well as we need to go for post-processing for metallurgically, we need to uplift the material for the required performance. When we think about the, it's a very high speed because it can deposit 9 kilogram per hour, but its price is very cheap because if you think about the cost of wire. So these are some of the applications, right? So what we have to think about is the additive manufacturing. I told about at the end of the presentation. What I actually want to say is additive manufacturing is not known to be given a inferior kind of a technology, but there is a long way there. We need to develop the additive manufacturing for some kind of application. That's what I want to say about. If you see here, the metal water connectors for Audi engine were 3D printed you can see over here another major issue. If you think about here, you can see these. There are some honeycomb structures, or some structures have been constructed from the base plate to the component. So those things are your support structures. The support structure, whatever the support structure over here, you need to design the support structure depending upon the component's complexity and the plane of presentation of individual layers. We need to construct, or we need to prepare some support structure to overcome this kind of a component. So this support structure design, we need a lot of softwares. I was also working with one of the scientists from CPET to do some of the support structure design softwares. Now, at present, for an example, if you want to use, there is a software called Materials Magic, sourced from Singapore. In NIT Trichy, we have a 3D printer machine for that. It costs around more than 10 lakhs for a version of software. So that it can help you in designing this kind of support structure design when you go for a powder-based additive manufacturing. There are a lot of more parts available for to revolutionize this additive manufacturing into automotive industries. When we talk about applications in case of turbine rotors in aerospace engineering, you see most of the repair works. Earlier, you can see over here, some repair works has already been done, right? Repairing that particular point and then again machining. You can also see some laser-based deposition is taking place over here. And these are some of the wire-based deposition process to correct the wear and tear of repairing a damaged part. And these are built up. We are this is an additive process. We are going to add some more material in the materials where it got worn out, and then again we will deposit that material and then we will machine it. These are the things wire-based AM repairs have been done. And these are some of the other areas of near net shape technologies like manufacture, repair, or it can be used for either surface treatment or rapid prototyping. So all these things, most of the areas are being covered by this kind of an additive manufacturing. Let us slightly discuss about the electron beam wire additive manufacturing. This is another part. So wire powder-based additive manufacturing is you have to spread the powder, use a beam to create one layer and layer. Here, we are going to introduce like your electron beam welding. We are going to have a wire feeder, and then we are going to have a source of electron beam to melt it, deposit layer by layer, so that you can create whatever the shape that we want. So this is one of the setup, right? A wire spool. You can see over a wire spool available here. The wire is being fed through some guideways, and then the wire comes out here, and we have the electron beam source focusing downwards, and we have to have a CNC system to move your component in the X, Y, Z system. And you can also use multi-axis robots for making any kind of relative motion to obtain any kind of a shape. It's possible with electron beam wire additive manufacturing. The advantage over this wire-based process is I told about very high deposition rate of 9 kilogram we can deposit, and moreover, when electron beams are used, usually we will be having the component kept in a vacuum environment, which assures cleanliness. Most of the aerospace components and other high reactive materials like titanium, if you are using it inside or depositing inside a vacuum, you will be having a very greater advantage of. It's an important factor which is most essentially for aerospace applications. When disadvantage is cost of this machine. For example, the machine what I show here is being procured in gas turbine research establishment Bangalore. It costs around 17 crores to bring the machine to on the floor to that particular industry. So electron is a costly equipment, and there are the size of vacuum chamber. Suppose if your component is of very larger size, very large engine blocks of very heavy engines, and we have to make the total chamber to be vacuum. So that itself will make a lot of time, and then creating the component inside. These are some of the disadvantages. So quite a lower cost type of an additive manufacturing we can perform by wire arc additive manufacturing. You can use a wire and you can deposit layer by layer by means of a MIG welding process, or you can have a TIG welding process, any kind of a material wire melting and deposition process using a CNC system. You can usually create this one. The advantage over here, this process, when you compare with the electron beam process, is there is no we don't want a chamber, a vacuum, or we don't want this kind of an environment. You can easily do it in the open space, but a very simple and cheap process. And the disadvantage is the properties non-homogeneity. As I told you, bead over bead, if you do, you will have some non-homogeneity metallurgically, which modify the properties mechanically, it will be getting modified. So the control of material deposition is another hectic process, right? So for example, usually when we are going to deposit some material to create these kind of features, you can see over here, these are wire-based additive manufactured compound features. So you can see the weaviness, right? There are weaviness here because of the layer to layers can be easily visualized. And you imagine if you are going to manufacture a component with this many size, this many surface weaviness, it cannot be directly used in most of the conditions. So you have to go again for a subtractive process. What a subtractive process can never be thrown out of the domain of manufacturing engineer. We have to depend on surface machining. Again, you have to go for rough machining and fine machining, and then you have to go for surface finishing processes, super finishing process or something else you have to depend on. This is about the electron beam additive manufacturing in action in that particular machine, what I told. And so the process of wire-based additive manufacturing highly rely on the shape of the beads, right? We are going to create one bead of material deposition. Again, we are going to create another bead of material deposition. In a way, it is going to give layer by layer deposition. So that's why the weaviness. So there are some research people are targeting and working on. What is the parameter and what is the geometrical correlation? So you can see with the same machine, with the same material, we have obtained two different kinds of bead geometries. So in the design for additive manufacturing should also consider this one, which will be affecting the geometry of it. And we do have done some of the dimensional measurements of single beads, so that you have to, for example, if you want a thick wall you want to construct, you have to go for the broadest deposition. If you want a thin wall, then you have to go for the narrowest deposition what you can perform. So there are very few researchers have done this work, and a lot of people are working on that one. So this is a few sample snapshots of electron beam additively manufactured. So you see one different parameters of the parameter 1 gives this kind of geometry, whereas 2, this parameter set of 2 gives this kind of deposition of a single layer. And you think about, you can see about the third one. So it gives a lot of too much of melting over there and tripping of the molten metal under the base. So so these are some of the things we have to take care about. So the optimization of a parameter to get that the particular geometry is another task, and a lot of research is going on, so that any material, what is the parameter need to be set for a particular width of wall deposition. You can see over here, to obtain a component like this, right? The first stage is creating by additive manufacturing, then go for a subtractive manufacturing. Recent days, there are hybrid machines, right? In a same CNC system, one deposition head will come and it will deposit. Another machining head will come and it will machine, right? You can check through a lot of videos are available in the www. You can check through that also. So another challenge is when we are going to deposit this material from one, for example, in the left to right direction as shown in the screen. So the start, the height, if you check the height at the start point and the stop point, there will be difference because of we are going to move the from left to right, stay there for a few minutes, and then you have to go from right to left, retracting the deposition torch. So it can have, so for this to overcome, some people are trying with directional change, right? First deposit from right to left, deposit from left to right, then right to left, left to right. So these are some of the research work are already being, people are performing. And this is how in an electron beam additive manufacturing is being used to construct some components, right? You can see over here, this is a wire feeder and the wire coming out of the wire feeder. And this is a built geometry. And you have the layers are, so for better understanding, I have taken here a Cartesian coordinate of x-axis, y-axis, and z-axis. And the wire moves from along the x-axis, right? And then the layers are being deposited in the direction of z. So once the component is built, we thought of finding out how much non-homogeneity exists inside this one. So for that, we use this particular material for a research work, a CNC electron beam additive welding machine being used as an additive manufacturing setup. And these are the process capabilities of that particular machine. And then some of the components have been done for one of the research by gas turbine research establishment. So we thought of extracting some samples like this, right? A sample oriented in the along the z directions, some samples oriented on the x-axis, some of the test coupons being made in the 45-degree to the xy plane, some along the y-axis. So there are 4 sets of samples have been extracted from these 4 different kinds of depositions, and then these extractions are being carried out. So you can see the build geometries built for various different processes, and using a wire cut EDM machine, we have extracted the samples along these directions, and it was subjected to tensile testing, and you can easily see that, right? So the area under the tensile curve gives the toughness. There are when the winner is that z-axis is what is that standing direction, right? The material being extracted all along the layer laying directions, layer built up directions. So there are a lot of reasons we thought of finding out why there is a change in the different directions. So any component, if you want to build for a automotive engine or something else where you are going to have different kinds of forces playing over, you got to we got to be very careful about choosing what direction we are going to orient the component, or in what direction we are going to extract the component. So let us. So this is what I thought of discussing about wire based. The next one is this one is the NIRBE, right? An unmanned air vehicle. Here in this NIRBE, you know about. I think most of you know about its range of 1,500-kilometer travel, and you can think this is a engine available inside this. I'm not decoding anything else. Actually, it's available in Twitch, and I'm using it for the explanation, right? So this is a small turbofan engine. This small turbofan engine is the engine used in that that unmanned air vehicle, that what that NIRBE missile. So here you can see over here a box like container. It is nothing but the starting nozzle. Usually for crank starting this kind of a high turbo engine, we may be using something a propulsive starter, right? We have some propulsive material compacted in a small nozzle chamber, and then we ignite it. So there will be a hot gas coming out with a very high velocity, and those will be hitting on these rotor plates, and then the rotor will be rotating. So we need almost 30,000 RPMs of rotation of these kind of rotor blades for this kind of a flying machine, where it's a we are going to form the trajectories. So in that case, these things are. I will play a small video for this one, right? So hope. So that's a process by which most of the automotive aerospace components, three-dimensional components, are built. So we see that the video shows it's we give a command, we have the object sliced, and you can have the manufacturing. I was also happy to see that. But NIT Trichy Center of Excellence in Manufacturing has got one 3D printer, and Dr. Dureselvam, being a chairman, he purchased this one for some 10 crore rupee. There is a equipment. But what happened when we are going for 3D printing of whatever the material? The one major thing is any additive manufacturing or 3D printing machine. So whatever the powder being provided by the manufacturing of the equipment supplier, we need to use it. If you use some other powders, you may end up with different kinds of complications. So one is because the layer, you see, one layer of powder will be some 40 micron powder. We will be creating one 40 micron layer, and then you lower the bed and again 40 micron layer. So in that case, suppose you see the figure number 1 here. What happened actually? This is something during the halfway, it got detached from the base and it got wrapped. So what the powder being spread by means of a very fine blade, it may made of a rubber or some polymers, and that blade or the wiping blade mechanism will get damaged. It will go to some few thousands, or it may go to lakh rupees for replacing this kind of equipment. So this is the required deposition. Here, see here in the right side, to make this kind of a shape, right? This is the component being manufactured with the optimum parameters in the right extreme. But this component is during the process of finding the optimum parameter, if you are not supplying properly, or if you choose the material not wrongly, or if you choose something else, if it is not done in the proper parameters, then you will end up with this one and the total machine will get damaged. This is again. So, for example, in NIT, we got some few materials, titanium Ti-Force, Ti-64, or aluminum ALSA10mg, or stainless. Is my screen visible?
Yes, sir. Yeah, you are visible now.
Yes, sir.
Okay.
Yes, sir.
Sorry. So we need to buy the parameter also. We have to pay parameter for individual material, then only we can use it. This is another major hectic thing, right? What we are supposed to face with. Sir, am I audible?
Yes, Professor, you are audible, but the screen got frozen.
Oh.
Network maybe slow.
Sir, is it okay now? Sorry, I think it's slide is moving, right?
Yes, sir.
Yes, sir, sorry. So the parameter again is very important, right? So these are some of the things, the challenges in powder-based additive manufacturing. So hope I'm taking too much of time. I will slightly skip some of the slides because of the technical difficulties what we faced. So the one need to understand in case what we have to know about is the characteristics of the powder is very, very important. When you actually this additive manufacturing is nothing but an advanced process of your powder metallurgy process. So what is powder metallurgy process is a very good old process where you see powders are being mixed, and then whatever the different kinds of components that you want, it is pressed into the required shape. Then it is kept inside a furnace for heating it to bond the powder particles. Thereby, large amounts of small intricate components has been manufactured very long back. So very little material. So this is so you usually parts for automotive industries or household appliances, different applications by metal powders which cannot be easily machined or melted, casted, tungsten carbide. These powders are being used even in Trichirappali ordnance factory, heavy energy penetrator factory. What they do, they use tungsten material to create rods of tungsten for using their penetrators. So those things are made with powder metallurgy, and the process of powder metallurgy is well established, like mixing the powder, creating to the required shape, and then sintering it, heating it so that the powder particles get fused, and then we can go for different process. So in these powder-based additive manufacturing, the major the property of the component highly depends on some of the characteristics like chemistry of the powder, purity of the powder, particle size, size distribution, particle shape, surface texture, all these things. So any alloy powder can be converted into any alloys can be converted into powders, whatever the combination. So, but whether in a 3D printer, a metal 3D printer, we have all the parameters for any kind of a mix of an alloy? No, 100% it is not available. There are very few research capability available with some few of the 3D printers. They will experiment and they will find out what is the parameter with which they can melt or add particle to particle, and they work on. So how the purity? See, if the so when we talk about the powders, the powder by the process by which the powders are being manufactured is very, very important. For example, this is an atomization process where you see the molten metal is being poured inside a small tundish, and through a small hole, the molten metal will flow. And in a controlled atmosphere, if you spray cold air or water all around, you will have separation of particles. Like if you blow a candle, right, you will have the molten wax spread into small particles, like the way you can have. Or sometimes you can have a consumable electrode, consumable metal being spinned off in a spindle, and you have a non-rotating, non-melting tungsten electrode, create an arc between that one. So the material will melt, and due to its high rotational RPM, centrifugal forces, the particle will get disintegrated on the periphery, on the radial surfaces, and you can collect it inside a chamber by creating cooling it down. So this is an atomization process. There are plenty of processes like chemical reduction, electrolytic deposition, pulverization, thermal deposition, precipitation from solution, or condensation of metal vapors. Any metals can be converted into powders. So this technology is already developed. So if you could see, depending upon the process by which you create the powder shape varies. Either so you can see something in these are all two-dimensional powders. It may have acicular shape. When you use a chemical decomposition method, you will end up with an acicular shape, or irregular rod shape, or a two-dimensional flake shape, or a dendritic electrolytic deposition method will give you a dendritic shape. Or you can have three-dimensional shapes like a spherical shape, or a rounded one, or you can see a porous, you have small holes inside, or you can have a irregular shape. So the shape, again, if you plot the particle size, right, if you take the frequency of particles, this is the particle size taking in the number of particles in a known quantity being in the y-axis. If you take the size of the particles, one should have something like a normal curve, right? So what we need is the small particles in little number, the medium size particle in very high numbers, and the large size particles in little quite lower numbers. So this is this kind of a normally distributed shape size particles. If you use, you have adjustments. What's that one is, suppose for example you take a container, right? In a container you put larger size balls. So if you put large size balls of same size, so you will have a lot of cavities over there, right? You will have a lot of porosity will be there. Suppose if I'm going to spread particles of larger size, smaller size in a container. So what you can have is you can have uniform filling. So this is how something called as an apparent density, how you are going to fill the powder particles. You can easily imagine about this one, right? If you are spreading same size particles, or if you are spreading smaller to larger, like a normally distributed size distributed particle, if you spread, the spreading will be very more uniform. So how to manufacture it, how to find the size, how to mix it, how to bring it, so that's why it is very expensive. And the particle shapes, so suppose if one powder particle spear to spear, its position is different, so interlocking will occur, right? Some internal success, for example, one particle need to slide with the other particle. If it is having very it has some crust and trough, you have irregularities on the surface, another powder particle cannot slide over that if you are spreading the powder inside a chamber. So this is very essentially important. So the surface area, all these things matters about how you are going to spread the powders. So usually we do, these are some other process, right? Roll crushing the metal powder into smaller powders, or ball milling or hammer milling, you can create powders. So when we buy a powder, we need to look at how the powders, what is the powder's flow rate, what is its apparent density, what is its compressibility, green strength, all these things one have to look. This is a sample sim image of a powder. You can see the distribution of the powder. Taking this marker as 100 microns, you can see this is more than 100 micron, less than 100 micron. So these are irregular. So different sized particles are to be brought together for having an apparent density of high apparent density. You can easily spread it over. Then mixing of this powder is again, right? Sometimes, as I told you, if you are now, the powder metallurgy technique is a very good technique where you can add any kind of powders. For example, if you are going to create an alloy, there are limitations. You have to go for a binary phase diagram or a ternary phase diagram. How many what is the system, how to develop, all these things matters about. But here in powder blending, you can take 50% of copper, 50% of aluminium, or 10% of titanium carbide. You mix it together and you can create a consolidated shape by consolidating all this powder, and you can melt it with the lowest melting temperature with which it can sinter, and you can create some components. So you got to mix it uniformly. We have a lot of physical and mechanical properties are depending upon the mix. So it need to be, see again, now in the 3D printers, when you are using powders, we have to wear some masks. These masks should get protect your powder particles. If the powder particles are less than few microns, 40 microns, it can easily float on the air. Usually the nano powders can float in air. If you inhale it, it can go and soak in your alveoli sacs, leading to a lot of respiratory disorders. People may die even. So in that case, you need to have a lot of hazardous environment. You got to be very careful about that. And then you cannot blend in air. So sometimes you got to blend it in an inert atmosphere. You may need a toluene like liquid. You have to fill. Then when we want to have a very good mix of this powder, right? Different alloys we want to make. These are different shapes. This is one available. You can see a double conical container where powder is feed from the top. You close it and it will rotate about the horizontal axis, so that this is the shape. So what you can see easily, you can blend the powders. Either you can rotate about a cylindrical, you can use a cylindrical vial or a container, or a cube vial rotated about its axis, sorry, diagonal, or a double V type what's the blending bowls. So after the powders are mixed, usually in the conventional method, what they go, they press, they roll, or they extrude, they are injection mold or isostatic or hot isostatic. Also some of the glimpses. So the loose powders are now applying pressure to create a component in powder metallurgy technique, either by using a mechanical press. You can see, for example, if you want to create a small spur gear with a helical hole inside, so there will be a punch, upper punch, there will be a lower punch, and this is a die inside which you fill the powder like this. The upper punch moves down and the lower punch moves up, and then you can create a consolidation of the powder inside, and then it is ejected. I'll show the cycles, right? Powder filling, compaction starts, compaction completed, component ejected, and then it is taken out. You can have, so what happens when you are putting powders and stacking, the powders are compressing the powder inside a closed container. Initially, there will be a lot of loose powders, lot of cavities you can see, spores, and then you can see it is getting restacked, and finally it will get deformed. So what the now see the additive manufacturing setup is usually not only powder spreading. Some of the technologies are now under research is you can roll these powders to create a uniform thick layer. So 40 microns, you can roll the powders before it is being heated. So that when you are rolling it, so this rolling based bed fusion process is on the way, right? People are working on that one. So in that case, you need to understand, see, this is what scientifically, if you think it is having a lot of difficulties or challenges in handling these kind of small powders. This is a conventional powder metallurgy, compaction, sintering process where you see a shoe like a powder is filled inside a container, a die, and there are relatively moving different parts, right? You can see over here. Why? Because if you apply pressure in a static powder from the top, you will get the density will be a little higher at the top and there will be poor density in the bottom. If you apply movement on either from the top and bottom, you have density variations all along the axis. So it is higher density at the top and bottom, and in the middle we may get a poor densification. And this is how different die movements, right? Punch and die systems can help. In this case, see here there are 3 moving parts. So this kind of a design for die can help to create uniformly, almost close to the uniform or homogeneous distribution of particles, so that we will not have a porosity at somewhere located. So for that, you can go for an isostatic pressing. You can put a chamber of, you can apply pressure all along, and now we can fill the powder. For example, this is a small tube component. So this is a this central core rod is meant for the creating the hole core rod, and there is a stopper at the top and stopper at the bottom to hold the powder inside this flexible red tube. And inside the powder, if you keep it inside a closed container, where you see we increase the pressure and cold isostatically pressing, and you can create the component. And this is instead people are making hip hot isostatic pressing. The powder is being filled in a required shape of a can, and then totally it will be kept inside a fluid bath where temperature increases and then stays for some time, and then it is reduced, and pressure also simultaneously increased, kept for some time, and then reduced. So hot isostatic pressing. So here I want to mention one important point. The powder-based additive manufacturing components cannot be directly used, because I told you the particle sizes are different. Spreading of the powders can create some cavities. Layer to layer, they may have non-uniformity over the powder particles distribution. So at that condition, there will be some porosity will be there. You cannot have 100% densified components usually. So what they do, they take the component, put it inside this hot isostatic pressing. After the component is being removed from the base structure, they put it inside and they do a hip process, hot isostatic pressing. They will increase the pressure and temperature so that the component will become uniform, having a homogeneous property in all the direction. Then only it can be used for some high wear resistant component or any kind of a bearing materials. Powders can also be getting converted into the required shape by means of rolling. You can see, for example, you can have 2 rolls and the powder can be fed along in between the rolls, and you can create whatever the cross sections what you want. Or sometimes you can also pressurize the powder inside through a screw conveyor, right? Powder extrusion process. Powder can be extruded through a hole. The powder comes over here and it gets pressurized because of the rotating screw mechanism, and then it comes out in the whatever the shape that you want. Or sometimes people are thinking to have a deposition of, so you can have one powder, another powder, mixing it together, you can have a deposition. So this green, so there is another additive manufacturing, as I told you, instead of hot heating the component and joining it at a time like a laser or electron beam, there are few developments are coming out where you see you can use some polymer jets to attach particle to particles. For example, a glue like a structure, you can attach particle to particle. So the 3D component is having all the particles together by means of a temporary joint, by means of any adhesive or some material. Then you can put it inside a furnace and you can heat it. So that what happens when you heat it to 70 to 90% melting temperature of the material, heat it for half an hour to 8 hours, depending upon the size in an inert atmosphere. What happens? The particle to particle gets attached together. That's called as a sintering process. So what happens here? When powders are separated by means of spaces or free spaces here in the initial conditions, right? And then what at the contacting point, you will get some melting happens because of the heat transfer from one particle to another particle. Then it loses its shape over here like this. And finally, most of the white spaces are big. The particle sizes, shapes and size will get get changed, modified, and finally you see you will get your components with a full density nature. So this is how the particle to particle. See, now people are doing some research related to the particles. For example, if you have two particles together and if you heat it, so there may be some intersection, like the particle to particle melting will happen at the point, and you can see the center distances reduces because of the protrusion of one particle inside another particle. So here in this case, if these kind of a melting semi centering, the centering takes place, what happens? Your component may lose its shape and size. Whereas this is another way of having. See here, you see the center distances are not at all disturbed, but whereas only the outer layers of the particle gets melted due to surface tension, it forms a meniscus and then it will get fused. So for this, people are working either some metal particles are being coated with a lower melting temperature material and they fuse together, and it's also under research, right? Coated powder particles can be used for additive manufacturing. Nobody has done it up to my knowledge, nobody has done. So the advantages of these powder metallurgy processes conventional is elimination or reduction of machining, high production rates, complex shapes, wide variation in composition, wide property variations, scrap is eliminated. The disadvantage is inferior strength because of porosity, high tooling cost, and high material cost, station shape limitations, dimensional changes, density variations, and health hazards. So this powder-based additive manufacturing or creating a component is not a latest one, like what our new students are thinking, and they are running behind this one. Everybody, if you see anybody, if I visit most of the projects of any undergraduate students, they will say that, sir, I'm going for a 3D printing. Either it may be a polymer 3D printing or metal 3D printing. Maybe the technology is different. So in 3000 BC itself, Egyptians used powders, metallurgy techniques, taking the powder base and then creating the shape to make tools. In 1900s, tungsten filaments, 1930s, carbide tools, 1960s, automobile parts, 1980s, aircraft engines. Now, GE has printed its own variable density 3D printer. What is this variable density 3D printer? So, for example, we have a structure, right? We have a component. Let us take a small example of this water bottle. If I need some strength in the base, so I can print it with high density. And if I want, I'm not interested to have too much of strength over here, I can print it with a coarser printing so that I have a lot of pores available. I can reduce the density in the top and I can increase the density in the bottom. So the density variations can be incorporated by means of how many particles are attached nearby in the vicinity, and you can create any kind of a variable density 3D printing by this. So topology optimization you can do. In that way, if you do, what happens? Almost 30 to 40% of the weight can be reduced in this engine. They have attempted and they have done more than 40% reduction in the weight, because of which you can put these 40% of the weight of the engine in the carrier, right? So any framed structure, for example, you have an automotive design, if you are working on, you know about because of you can understand when you have a collision where the forces will actually get distributed. So those areas you can put a higher stiffed or high strength or high density. And there are some aesthetic shapes where we don't have any kind of any impact force is going to happen. At the time, you can have a coarser 3D printed components. So these are few examples of metal cutters, right? Edges of metal cutters, washers or something else made by powder metallurgy technique in very good olden days, right? There is an ASM handbook of powder metallurgy itself, right? Volume 7, I remember, so if I'm right. And you can check through these kind of components can be made by any intricate shapes. Now these intricate shapes, earlier they have made a mold, and now it's not required, right? You just want this intricate shape in your 3D model. You can create layer by layer. You can create any kind of excellent components, and any that's intricate shapes means, I told you know, any kind of a shape, even your lung, one can scan a lung in a biomedical, and you can print it, and you can create any kinds of, these are some kinds of bushes and different complicated. And this is the powder metal based tungsten light but filament, right? You can think about the spiral helical distance is 300 microns, and individual small what is the 40 micrometers. It can be easily done with a powder extrusion process. You can extrude the powder, and if you make the way so that it can be made into this particular shape. This is how. So along with some of our research team, we have also done some powder-based compaction sintering process, we created some copper, titanium oxide, graphite powders have been mixed, and we created some components, and we analyzed within scanning electron microscopy. Then we used it for electrodes for electric discharge machining. And these are some of the evidences really what a composite, metal matrix composites have been made. And we find a lot of property improvements when we include these kind of an additional second phase particles, right? A lightweight particle is being reinforced with a hard particle, high stiff or high wear resistant particle, so that we can improve the workability or its endurance life. And this different kinds of electron wire electric discharge also we did. So in that case, right, now if you have a complicated component, if you are making with a complex material, then how to cut it? If you use a wire EDM machine, usually the wire keeps on cut, right? It will break because of the non-homogeneous materials also. So that's how we have done some research although in that case, and we did how to cut it now. So the complexity becomes when the materials are getting complex by adding more than one kind of a material, then its machining process also gets difficult. So one of the way, even I could see some IIT process during my interview also, right? They were questioning me, right? What's the idea about creating a composite material, metal matrix composite? More than one number of material is being mixed. How to make a 3D printing? It is again a challenge, right? Some of my research students are working on in a wire additive manufacturing. They create a wire by composite, and then they use the wire to make the depositions. It's also possible. So 3D printing, as I told you, it's not a newer process. Even in 80s, right? And you can see in 1990s, in late 1990s, there are some machines called a 3D system centralization. So these are some SLS pattern runs out in February 2014. So these are some intricate shapes, right? What you can see, you can create using, you can't even imagine. No other process can be used to make this kind of a very complicated shape. To show about its complexity, this is being printed using a selective laser melting sintering system. And the production department in Trichy, along with myself as a PI, we have taken something like, as I told you about the starting nozzle initially in that engine, right? That starting nozzle has to withstand around 2000 degrees centigrade in a convergent divergent nozzle. And we did some analysis, right? So by printing the component in horizontal axis, angular axis, and vertical axis, and then we did some X-ray diffraction analysis, scanning electron microscopy analysis, energy spectroscopy, and then elemental analysis. And based on that, we have also seen something like the measured density and the theoretical density. We found the relative density of component being printed horizontally, vertically, angular, and then we compared with the conventional investment casted component. See the component I told you about, that starting nozzle. That starting nozzle is a complicated shape. It earlier was made by investment casting technique. Because of its complicated or intricate shape, when 100 components are being printed, they found only 8 components qualified the dimensional measurement. So what they did is they thought of going for an powder-based additive manufacturing. And myself, along with another professor, Dr. Duresulom, we took this as a project to find whether it is the feasibility of additive manufacturing for the manufacturing of that starting nozzle. So this is a project worth around 10 lakh rupees for 18 months. So these are the different hardnesses what we get. So here the casting wins with the higher hardness, right? Either then we went for a tensile testing for the horizontal component, vertical component, angular component, and investment casted one. And here what wins, right? You can see the tensile strength of the 3D printed components are almost nearly twice that of the casting. And moreover, you can see the average elongation of these components, percentage elongation also very high, more than 2 times. So it's a very highly recommendable process by which you can go for additive manufacturing. So we have also found out what is the reason behind the additional improved tensile properties of this particular 3D printed components. We investigated the fractography from the fractured components, and it has been reported. And as I told you, the material has 1.16 times the yield strength of the when compared with the conventional material. And these are some of the research works what we undertook based on this additive manufacturing. You see this, that's what I told about the small turbofan engine for this missile, and this is the turbine blade, turbine rod, and you can see the starting nozzles shape. And these starting nozzles are manufactured by investment casting, and they find it difficult. And then When it is 3D printed, then you can easily obtain a lot of acceptance. This one kind of a work. And there are complications of this kind of additive manufacturing. After making additive manufacturing, if you want to make some cutting process, we can rely on this abrasive water jet machining. And this is another important work. What I want to show, this is an aircraft engine blade, right? This aircraft engine blade, the drawing is shown here. What you see here, there are inside this, you cannot see by naked eyes. There is a small 3 holes over there. Inside this structure, there are plenty of hundreds of holes. So the when this turbine blade is rotating, right, cold air will get inside this particular hole, and it will circulate here, right? You can see the cold air inside going inside and circulating and coming out, so that you will get the blade cooled. So for this, after making the process, they want some of the holes need to be blocked by means of powder, compacted, and then by brazing process. So we have taken this project for around 19 lakhs from Gas Turbine Research Establishment, Bangalore. And this is a fixed design. And we plan to make this. See, think about this is the pellets we have to make with the different kinds of composition of materials. The material has to be made for 2.5 mm diameter small pellets. Most it's very close tolerances. Then it has to be kept like you can see this animation. These 3 pellets are to be kept inside these 3 holes. So we have planned for a what is that, a boroscope to keep that one intact, and then we will keep all these things inside a furnace. So this is a currently ongoing project. Actually, we are shortly closing that particular project about that one. And when you universally, if you think about, there are challenges. Why these challenges come to picture? So there are a lot of material development is being carried out all the way, right? You can see polymers apart from, so metals and polymers you can combine to give some different properties. You can combine metals with ceramics here, or you can combine ceramics with polymers. These are more than one material combined together to give the desired properties, what we call it as a composite material. In these composite materials, there are a lot of researches going on how to manufacture the composite material, one. And if you manufacture, I told about in additive manufacturing, if I'm going to mix, for example, aluminum and titanium carbide inside, so what is it melting, or the parameter going to be set by the laser to create the component becomes a challenge. And again, if these composite components are made, how to make a hole or something else? There are 10⁶ kinds of materials, and individual material has a lot of hundreds of properties. It has like density, its coefficient of thermal expansion, its compressibility, a lot of things. And then so there are a lot of process. You need to choose the particular process for making the component for the required. So the challenges are there. So if you overcome any one of these challenges, right, it can lead to innovation. So challenges are there. If you do the challenges by means of your routine work or any kind of a new idea, combining hybriding different kinds of technology together, one, you can end up with these kind of innovations. So these are some of the other research areas. What we did, a metal matrix composite by in situ casting. It's one of the cheapest technique by which you can introduce two different powders to make composites. Few of my PhD students did their work over here. We created some powder metallurgy based metal matrix composites, and then we did some like so what we can do in future, you can develop new materials by using the recycled material you can use, and you can develop unconventional technologies for machining that one. So new material comes, then there is a new process need to be identified for machining. And by friction stir processing also, one can create this kind of powders can be fused inside any kind of thing. And there, to develop newer materials, we can use additive manufacturing by friction stir processing is another part, right? You can have one sheet of material or one piece of material and another piece of material. You can use a stirring to merge or fuse these two material, and then you can keep another piece of material, and you can do any kind of a sandwich kind of. So this friction stir processing can give you usually this friction stir processing is best for friction stir welding, or friction stir processing is better suitable for different materials, varying materials one to another, dissimilar joint. So you can have one layer of aluminum, one layer of stainless steel or something, another layer of aluminum or magnesium, like that. You can have different kinds of layers of material to give whatever the requirements that you want. And this is additive manufacturing by SLM. I told about this process. And usually one more study what we did is currently a few researchers are going on. You have some components are being printed like this, right? You have components are being printed. So to check the challenge, what I did, we just made a nut and bolt, right? we created a nut and bolt for this using this powder-based additive manufacturing, and we tried to make it right. You cannot make the uh, make the nuts and bolts working together as like what you have machined. So this is because the additively manufactured components, right? If you see, the additively manufactured component will not have the surface properties as like of the one what we do in a conventional machining process. So this is how we are doing some research with the surface properties, the directional oriented surface properties. Very few studies have been done. So you can do some additive manufacturing and you can evaluate the dimensions. You can measure the dimensions, and then based on the surface roughness and the dimensional variations. So for that we do a video measurement system is being used to find out that one, and we are doing it. And this is wire arc additive manufacturing. I already told about some of the one or two students have done it. So to develop technologies for dimensional control. Now, as I told you, how to control the dimensions, right? You can see how to make the required shape exactly. There are some machine learning algorithms or AI systems are being nowadays used to predict if I use this particular parameter, what will be the width of deposition, so that you can control over the flow of the material to create whatever the kind of geometries. That is another area. So we can develop a lot of these kind of things in future. And again, electron beam additive manufacturing also the same kind of issues are there. If you just look at electron additively manufactured components, right? These electron beam additively. So sorry. So this is again additively electron beam additively manufactured components. You can see the weaviness, right? You can see this is not so smooth here also. So this is how again there should be some technology to control these dimensional properties of this electron beam additive manufacturing. Or if you want to do composite by means of electron beam additive manufacturing, also there are a lot of openings. And then finally, so all the features cannot be additively manufactured. Sometimes after making this kind of an additive manufactured component, when we are taking it for cutting a sample, even we cannot cut it, right? So we need to understand about how to machine it, right? How to machine it or how to cut to the required shape after being deposition. Then we can use either unconventional machining like abrasive water jet machining, or electron beam machining, or electric discharge machining. Usually wire cut EDM machine even won't work on that. So our wire EDM operators are afraid. Whenever we take a additively manufactured component, they will tell, sir, please go and do some conventional machining on the surfaces and bring it, or otherwise my wire gets disintegrated. Again, I have to work on that one. These are some of the difficulties faced in, these are then about this additively manufactured component has different kinds of tribological properties. Friction. If you are going to additively manufacture some piston rings, reciprocatory material, then you have to study deeply about the friction behavior, and then the what is that, the wear behavior of that material. So we have done some work also. So to develop newer materials, or the process is modified, or the new kind of a composition is being brought to inside, then that's a challenge. So these are a lot of challenges what I told about. I think I'm sorry I have taken too much of time. There are there's a center of excellence in manufacturing in NIT Trichy being inaugurated in 2018. I have two slides to show. It was inaugurated by the Prakash Javadekar, the then Minister of Human Resource. And we are signing MOUs with the different kinds of institutions, education institution, industry sign MOU with Siemens Center of Excellence. Now it is being called as Center of Excellence in Manufacturing. And we have a lot of facilities like softwares for design validation, advanced manufacturing simulations, testing and optimization, robots, CNC machines, prototyping, rapid prototyping, additive manufacturing. Along with that, we have the robot training, all these things. 3D printing is also available with that one. So anybody interested can utilize the facility. This was just for an introduction. So what is happening in the Indian industry is manufacturing is impressive in growth. There is advantages of globalization, interesting overseas acquisitions, entry of prominent MNCs in India, salary of manufacturing at entry level, those exceeds in IT sectors. Now it's being you can see more than IT sectors, people are getting some good salaries in that. This is based on some input from NIT placements. So there are enormous challenges in materials. One is design of material, new material has to be invented, and then the processing material, manufacturing process, either by an additive manufacturing or subtractive manufacturing. So far, I have told you a lot of difficulties that we come across when we are going for an additive manufacturing that need to be solved, especially for additive manufacturing. So it is open. When there is a lot of problem, the engineers are quite in a lot of engineers are required, scientists are required to solve the problem so that we can solve all these problems for the next generation to move in a different way, so that we can do a lot of things to make the country developed country, always with all the manufacturing technology being carried out inside the country indigenously. If you could manufacture, then we will shine in the world, as like what India was named for the manufacturing of vaccines. We need all the technologies. So for that, I think if the students or anybody is ready with the enough knowledge, what to do next is they need to go for a presentation in a symposium or a conference, so that some critical ideas they can acquire, and we can also ask them to then, including the critical criticisms of the experts, it can be addressed, and then it can be submitted for a book chapter or a journal, or sometimes it can be taken for a patent if it is very innovative. And usually now startups, right? Startups, there are a lot of funding being provided by government agencies, government of India for startups. I have come across a lot of my friends, and I have been a part in some screening committees also. Plenty. If there is a patent on your own, if you have your own idea to manufacture any kind of a component, and then you will get endless support financially from most of the agencies, whatever it may be. So I think thank you very much for this very late lecture. I have taken for a long time. Thank you. So this is my email ID, krishna@nat.edu. So if you have any questions now, it's open, sir. Sir, I'm audible. If it's open, any questions you can raise. Thank you very much. Sir, I'm audible.
Professor. Hello.
Sir.
Hello, Professor.
Yes, sir. Yes, sir.
Okay. Sir, so is your part over?
Yes, sir. Can I stop the recording, sir?
Yes, Professor. You can stop the recording. So
Okay.
officially, I thank Dr. Viananda Krishnan for giving this wonderful lecture. So we are very much thankful for sharing his expertise. So hope your services will be continued in SAE Trichirappali division in future too, sir.
Thank you, sir. Thank you very much, sir.